So yesterday we have started with mathematical development of linear discriminant analysis. We will proceed with the same. So let me share my screen. So yesterday we are here. And we have talked about the confusion matrix. You have two categories and you are predicting the classification. So if a flower from Iris setosa is classified in Iris setosa itself, then that probability is probability of 1 given 1. That means an observation of first category is classified in first category itself. This is the probability of correct classification. An observation from Iris versicolor, a flower from Iris versicolor, if predicted as Iris setosa, then it is probability of 1 given 2. It is the probability of wrong classification or probability of misclassification. If a flower is from setosa and if it classified as versicolor, then that probability is probability of 2 given 1. It is also an probability of misclassification. A flower from versicolor if classified as versicolor itself, then that is P2 given 2, which is a probability of correct classification. So it's a 2 by 2 matrix. It's a 2 by 2 table. And in this 2 by 2 table, there are 4 probabilities. Out of these 4 probabilities, 2 probabilities corresponds to correct classification and rest 2 corresponds to probabilities of misclassification. This matrix is called as confusion matrix because the total of all these probability will add up to 1, and this will give you the idea about how long you are correct in classification and at the same time how long you are misclassifying. That is called as confusion matrix. On the parallel line of confusion matrix, we will write the matrix of cost of misclassification. What we'll do is we will write the cost of misclassification. So let us see here. I will give the another name, cost of misclassification. Cost of misclassification. Okay. Now we'll work with the same thing. But before that, let me give you an example from medical science. If a person does not have any disease, and if you predict that yes, you have certain disease, that is misclassification. On the other hand, a person has a disease, but you are declaring that yes, you do not have, you are normal, you do not have any disease. That is also a probability of, that is also a misclassification. Now these two misclassifications does not have equal importance. They do not carry equal weightage because a person having disease, if declared as a normal and if it does not given any treatment, then he may be subjected to any critical condition, and that critical condition will lead to a heavy cost. Whereas A person that does not have any disease, even if given a treatment that may lead to some cost, but that may not be that much critical one. And that is why we have to talk about costing, what cost it is associated with. So let us see this setosa and versicolor case again. What is it? If a flower from setosa is classified as setosa, it is a correct classification. It means what? There is no misclassification, and correct classification will lead to zero cost of misclassification. Correct classification will lead to zero cost of misclassification because it's a correct one. A person having disease, if declared as you have, it is a correct decision, correct diagnosis, and so it will not lead to any cost because he will be treated properly. If a person does not have any disease, and if declared as yes, you are normal, you do not have any disease, then he may not be given any treatment, and hence he will not be subjected to any critical situation. So there is no cost associated with it. So in the second case also, we can say here C2, and this classification will also lead to zero cost of misclassification. Otherwise, if you come to the rest two, sorry, our table is this. Our table is this. Yes. If you come to the other two, say for example here, it is cost of misclassifying a second category object in first category. That cost may be whatever it may be, but there is a cost. What is this? This is the cost of misclassifying an observation from first category in second category. So this is called as cost of misclassification. Now we have probabilities, we have cost, so we can find out what is the expected cost of misclassification. So let us come to the next case, expected cost of misclassification, ECM. What is it? It is expected cost of misclassification. Expected cost of misclassification. Okay. Now we will see how to find it. It is very simple to find. It is very simple to find. We will find it. Okay. Now suppose I take this probability confusion matrix table to this side. Okay. I will write here actual class. Here predicted class. Let me write here say C1. Let me write here say C2. Let me write here say C1. Let me write here say C2. And let us forget about this. Just I want to add two matrices here. I have to write here C1. I have to write here C2. Okay. So see, this is the this is the probability matrix, misclassification matrix. Now let me copy this and I will write it here with this. Okay. Now ECM, I want to find out ECM. Expected cost of misclassification. So let us see. Let us see. P1 is the prior probability with which P1 is the prior probability with which an observation may belongs to class C1. An observation may belongs to class C1. Now you know that this cost is 0. This cost is 0. Similarly, you know that this cost is also 0. And so effectively speaking, the expected cost of misclassification will depend upon the probabilities of misclassification and cost of misclassification. So it will be like this, P1 into, so let me put star, P of 1 given 2 star C of 1 given 2. This is first term plus the second term. P2 is the prior probability. So P of 2 given 1 and C of 2 given 1. This is the cost of misclassification. Because with this cost, you are committing the this is the cost of misclassification. Try to understand this. Try to understand this. P1 star, P1 given 2. So P1 given 2 is the cost of misclassification, sorry, probability of misclassification. C1 given 2 is the cost of misclassification. Similarly, P2 given 1 and C2 given 1. So this is the expected cost of misclassification. Now, can you use your logic and tell me what is our expected cost? What should be the expected cost of misclassification? Do you expect expected cost of misclassification should be maximum or minimum? Do you expect expected cost of misclassification should be maximum or minimum. And it is obvious that it is the cost of misclassification, and therefore it should be minimum. We want to minimize it. We want to minimize it. Expected cost of misclassification. ECM should be minimum. ECM should be minimum. This is what we expect. Now, mathematically speaking, when we want to minimize the function, this ECM is a function. It is a function of prior probability. It is a function of probability of misclassification. It is a function of cost of misclassification, out of which P1, P2 are constant, cost of misclassification are constant, and these probabilities will change. So essentially speaking, expected cost of misclassification is the function of P1 given 2 and P2 given 1. Mathematically speaking, when we want to minimize it, we go for calculus, differentiation, first derivative, second derivative, solve the equation of first derivative, obtain the second derivative. If the second derivative is greater than 0, then we say that minima occurs. So that is the point of minima. That is what the usual process is. But in the present case, f1x and f2x is not clear-cut mentioned. If it is mentioned, then it is quite possible that we can go for differentiation. But it is not. And therefore, your traditional approach of minimization, that is calculus, will not work. We have to think of something else. And so, while thinking of something else, we'll make some assumptions. So let us see what are those assumptions we are going to do. Okay. See what assumption I am going to make it. I will assume like this. I will assume two things. Number one, P1 equal to P2, and that is equal to, of course, 0.5. This is my first assumption. Means prior probabilities are equal. There are equal chances that observation can belong to category 1 or category 2. This is first observation. The second assumption that I am going to make it is about the cost. This. Okay. So what are my assumptions? My assumptions are about prior probabilities and cost of misclassification. So what I am saying is prior probabilities are equal and cost of misclassifications are also equal. That is what I am going to say here. Okay. Now, as soon as I say this, my expected cost of misclassification will become, something like this. That it will go. It will become a constant. This is also equal. It is a constant. Why I am deleting this? Because they are constants. And essentially speaking, expected cost of misclassification is nothing but the total probability of misclassification. That is what that. Okay. Now, how to find this? How to find this? See here, how I can write P of 1 given 2. How I can write it? See, I can write it like this. Okay. See, this is what I will write. Because if you see the probability of 1 given 2, it is probability of observation belongs to R1, given that it is from pi 2. Originally it is from pi 2, but it belongs to R1. And so accordingly, this is the probability of 1 given 2. This is the probability of misclassification of 1 given 2. How I can write another one? I can write another one also. I can write another one also. And it is like this. It is now like this. It is not 1, deleted 1. Okay. These are the two probabilities. And we have to add up these two together. We have to add up these two together. So we'll add this. And let us see how the equation looks like. Now instead of this, I will add this. And instead of this, I will add this. I have to put it here. And I have to put it here. Okay. See the problem here. Integration of F2 on R1. Integration of F1 on R2. So solving this is little bit difficult. So we'll go for another slide where I will give you one trick. And that trick is this. That trick is this. This is the trick. This is the trick. Integration of F2 over the union range R1 union R2 is 1. On the similar line, we can write integration of F1x dx on R1 union R2 is 1. But these R1 and R2 are distinct ranges because distributions are different. So we can write this as follows. Oh, I am wrong. See how I can write it. This I can write as okay. This. Okay. This we can write. Integration of f2x dx over r1 union r2 can be split like this. What is the advantage of this? Its advantage is this. I will write the advantage. I will write the advantage. It's 1 minus and this is what I can rewrite. In the earlier statement, we have this. And that was creating the problem for us. That was creating the problem for us. So can you see what will be the possible replacement? Can you see what is the possible replacement? Yes, we can see the possible replacement. And that replacement is, instead of this, we can replace this. So let us come to the next statement, next slide. Let us come to the next slide. And we know that this we are going to replace by 1 minus this. See, this is the replacement. Correct? So we are going to replace it. The advantage of this replacement is what? The advantage of this replacement is the ranges are same, R2, R2. I think this is F. R2, R2. See, our time is over. For today, we'll stop and we'll continue tomorrow.